Now we will discuss the main program and subroutine architectural style that follows from the procedural programming paradigm. C is a language that follows this paradigm. Before we begin, be aware that you may find the terms routine, procedure, and function all used interchangeably with the term subroutine. Main program and subroutine is a style that is fundamentally focused on functions. When presented with a system to model, you break up the overall functionality of the system into a main program and subroutines. In the diagram, we can see how subroutines are connected by procedure calls, and may even have nested calls. In nested calls, subroutines may call other subroutines, which may call other subroutines, and so on. As you can imagine, the structure of the resulting code is not flat. It's hierarchical, so it can be modeled as a directed graph. The structure of the subroutines that build up the system affect the structure of the system as a whole. Essentially, the subroutines, as declared in the code, are structured as a big call tree. Data in this paradigm is stored as variables. Like object-oriented programming, procedural programming supports abstract data types. However, inheritance is not explicitly supported. It is not easy to make one abstract type an extension of another type. Unlike object-oriented programming, in this architectural style, your main consideration is the behavior of functions and how data moves through them. As a result, this approach is suitable for computation-focused systems. Each subroutine may have its own local variables. A subroutine has access to all data within its scope. To give a subroutine access to data outside its scope, data may be passed into the subroutine as parameters, by value or by reference, and data may be passed out of a subroutine as a return value. A principle that arises from this paradigm is one entry, one exit per subroutine, which makes the control flow of the subroutine easier to follow. This architectural style promotes modularity and function reuse. When your functions are well defined, you can think of them as black boxes. Given a particular input, you can always expect the same output. Additionally, rather than writing all functionality from scratch, you can easily integrate library functions into your programs. A potential issue with this approach is that subroutines may mutate data in unexpected ways. A subroutine may be affected by data changes made by another subroutine during execution. This issue is especially true for global data shared across subroutines. These changes to data can be unpredictable and result in a function receiving an input that it was not expecting, or even an input that it is not capable of handling correctly, which can result in runtime errors. Let's look at an example system that can be built from a procedural programming paradigm. Consider a spending management program that applies the main program and subroutine architectural style. Let's assume this program reports your spending. Not only does it keep track of the total amount you've spent, it also provides you with information about which categories your spending falls into. The main program and subroutine architectural style is particularly appropriate here because the overall functionality of this program can be easily implemented by smaller subroutines that each handle separate parts of this overall functionality. The subroutine responsible for calculating your categorical spending first calls a subroutine that parses through all your purchases, then determines the category each purchase belongs to. Then, this subroutine calls another subroutine to sum up the amounts spent on all purchases in each category. Next, from main, a subroutine is called to sum the amounts spent across all categories. Finally, from main, a subroutine is called to transform this data into a report which is printed to the user. In this lesson, we have seen how the main program and subroutine architectural style emerges from the procedural programming paradigm. This style promotes function modularity and function reuse by insisting that programs are built up from smaller subroutines. Systems centered around computation can be ideal candidates for this architectural style. In the previous example, an object-oriented architecture style would not have been as appropriate. Identifying object-oriented components of these kinds of systems can be arduous and result in overly complex solutions, especially when applied to simple programs. That said, depending on the problem, it may be easier to use an object-oriented approach. For example, if abstract data types with inheritance make modeling the problem easier, then it may make more sense to use an object-oriented architectural style.